Okay, my name is Kabelo. I am currently at Rhodes University. I do serve as a software and machine learning engineer for a research group, and I'm currently also doing my PhD there. My interest of work is developing machine learning algorithms, mainly focusing on graph neural network and physics-informed neural networks for drug discovery and understanding how reactions works. So today I'll be just going through, we'll be just introducing machine learning and doing some fast demos just to show you how does the machine learning work. So I won't do complicated stuff. We'll just start with simple stuff today. Yeah, as I was saying, today's session will be focusing on the practical understanding of the machine learning models and how can the data itself influence the model's behavior. And from there, we'll be also learning simple models up to ensemble models, which I will explain later. What do they mean by ensemble model? And also, I'll be trying to connect theory with some real world application. And of course, I won't go into much of mathematics as I'm saying theory. So as I was saying, from simple models, we'll be just going through an ensemble models, where mainly ensemble models just mean that now instead of using one model, you are using multiple model to solve the same, um, to train, which I will explain properly later as we go on. And we'll also be looking at why these models matters because they're easier to interpret and they can tell you a lot of things that you may have not understood within the data. And of course, we'll also talk about the limitations and why ensembles they're important, and of course, and which ones they are more good for the real world application. So, what is very important is before you can really go into the model itself, is for you to understand the data. Number one, how is your data being structured? Um, is your data values or your data is images? Is your data voice recordings? Those things, they matter before you can even start to say, um, I want to do a machine learning model. And also, what is also important is understanding your data. Is there a noise within your data? What do we mean by a noise? It's just that those values that they don't really going to help you, the model to learn anything at all. And sometimes when the data is too complex, we also don't know what is noise. And those things that are very important. And what is the uncertainty of the model? Of course, the model may seem good, but what is the uncertainty of it? And you also need to understand whatever you are training the model on, your data quality is very important. And towards your prediction, you cannot use um, different types of data trying to predict something that was not being trained before on the model. Why the model performance varies across data set is mostly based on the data itself and the quality of the data as well, and also the intuition of how to choose a model based on your data structure and the pattern. And of course, I'll be doing demos. I will do demo after, and I will run through it quickly. But for now, and also I'll be doing some brief introduction on neural networks. Why is it important for us to move a little bit away from ensemble? Why do we need neural networks and why they are popular as well? So just to give you a little brief of understanding why machine learning matters a lot. So before, what we used to have is that we used to have a traditional programming where you put many rules within the code, and when then you put your input, then now those input will go through your code and check if they meet the requirement. For instance, you are trying to write a program that can taste the quality tea. So what you will do, you'll just say if the tea is hot, that will be the first rule. Then taste it. But if the tea is cold, then put it in the microwave. Then already you have if statements. Those if statements, computing them, they can be very bit problematic in terms of time and the complexity. So then from there you start to say, okay, if the tea now is hot, then taste it. If the sugar is low, try to put 2 teaspoons of sugar and stir. Those are the rules that you put until you get to whatever you want. But those things, the moment you start to have many ifs, it becomes a problem each and every time you're trying to compute. And those things that are known as simulation. And of course, in real life, we don't really have those if alone. So you have real simulations that requires to solve mathematics behind, where now if you want an answer of a simple thing, you can end up waiting for minutes or hours, or depending on the complexity of the problem, where you are trying now to understand the market, or you're trying to predict the market using simulations, which can take a day if you don't have good computing system. Then now came a machine learning model, which helps a lot. What does machine learning do? You give it examples, then it learns the patterns. From there, you ask it question, then it gives you the answer based on those. So what it looks for is the patterns within the data. Then from there, what you're going to ask questions. That's the simplicity of what does machine learning do. It just learns from the example. So now let's go into what can you do with machine learning model. You can make predictions, whether you want to predict the prices of sneakers, or you can also make classification. What do we mean by classification? Whether you want to tell if an email is a spam or is not a spam. Those are classification. You have two classes, spam and not spam. You are trying to tell by looking at the email that you're trying to feed the model that to tell by looking at the email whether the email is a spam or not. The same way now these days on your Gmail, you just find many emails in the spam already detects that. So that's the good work of machine learning as well. Then you can also have clustering. Clustering is that you can imagine you have a spreadsheet that have so many columns and rows, and which are difficult to put in a graph to analyze everything in detail. So what you can do, you can just do a data compression where now you can analyze everything, and that is called clustering. And now you can tell which, however, when you are clustering something or you are doing a data reduction, you are losing some information, which the PC, which the model itself claimed to think that that is not necessary for you to have, which is a different story for as we go on. We'll just start with a simple understanding of the machine learning model. We'll choose linear regression. So linear regression, if you're familiar with linear graph, that was a linear regression machine learning model. So what you're trying to do, you're trying to fit a straight line within your data points. And from there, once you have the straight line, you can compute the equation, which is your mx plus c. Hence, you see the equation here. So, of course, here now when you're writing it, now we introduce the error term. How far is your data points from the line, which now we need to know, can we rely on the model or not? So those things, they are very important. And then this is your y value, and this is your slope. So once you have the equation, then what you can do, you can put the x value to get your y value. So what does this mean? It means that if you have the model, you can now, based on if you have a sneaker rarity index, then you can put it in within the equation. Then you will know how much the sneaker will cost. Even though the price was never there before, now you can put it in. So now you can predict how much will the sneaker cost. That's the simple machine learning model. But the danger of it is that it's mainly relying on linearity. So if you don't have your data linear, or there's no correlation within your data, then it fails a lot. So in those cases, you will need nonlinear machine learning models. So so this one is quite simple and it's easy to interpret. And of course, I will say if you can use it, please use it. It tells you many things, which I will show in the practical demo as we go on. It's easy to interpret and it's quite fast. It doesn't take time to run. So another model that I want to give us on is support vector machine. Here, what we are trying to do is classification. So support vector machine, what it does is trying to classify the data. So what you're looking at is trying to classify the data by maximizing the margin. So of course, this is not a real life data. As you can see, the data points, the red ones, they are far away from the blue ones. But in real life, you have this intercrossing each other, where now the model is trying to put a line in between where now it can separate the blue ones from the red ones, from the real data. But in some cases, you'll find that the blue ones cross the main line, which now they introduce the error. So which means now you're going to have a higher error compared to when if none of them they are crossing each other's borders. So it's like a bouncer. So what it does is just needs to separate uh, um, um, the kids who are not supposed to be in the club and the elders. But sometimes when you have many people as a bouncer, you tend to forget to check the IDs. Even the kids, they end up going inside the club, which means now what you are doing, you're introducing an error, which becomes a problem that now you are not reliable. But of course, you can't be reliable if you are working with so much complexity of the data. And this one, the issue of the support vector machine as well is that it relies solely on the straight line. So it cannot go somewhere, somehow, where it tries to fit itself in a nonlinear way. So that's another issue that it fails to do. So now I'm also going to choose another machine learning algorithm, which is important for clustering, which is a PCA. I hope I'm not going too fast. But what is a PCA? With PCA, what you're trying to do is you have a very complex data, and we're not talking about a simple a spreadsheet where you have 100 rows with 10 columns. We're talking about when you have 100 columns or maybe even worse, 1,000, which some people, they work in real life. So what you're trying to do, you're trying to understand how does the data work. So you need to reduce it. And somewhere, somehow in those 1,000 columns, you find that there are noise, things that are not important, values that are not important. For instance, if I'm trying to predict the sneaker rarity, and the information that I have as well is the um, is the is the name of the person who was making the shoe in the factory. Nobody's interested in that. That is just a noise. So instead, I'm interested in the label, whether it's a Nike shoes, whether it's those they can factor in, which they can factor and change the prices a lot. But nobody cares whether it was Kabelo, the factory making this shoe or not. So those things, the PCA, what it's trying to do is trying to filter them, is finding them as noise. But sometimes the issue is that it can remove important stuff, thinking that is a noise. So when you are dealing with PCA, you just need to find a way to reduce the amount of information you can lose, which I will show you in the practicality of it, how you can use it, and you'll see how the data is being lost. So those are just single models. They suffer a lot from something called overfitting. So overfitting is a term that we used in machine learning model, but what the model is trying to do is just memorizing. So when you give it a test, it fails. So it does not learn anything. Sometimes you find that your model is not good enough to understand the complexity of the data, then it's underfitting, meaning that your model is useless against this data. You need a proper model. So which are And some of the other things, there are blind spots where the model cannot get the perspective. That's where now these days we start to introduce things like physics informed neural networks or financial informed neural networks, where now you put in the equation and try to show the model that this is how the information is being derived, and this is how you can think about it if you lack the understanding of the data. So, which is very, very important. So now we're going to look at ensemble modeling. So ensemble models within machine learning models, that instead of just using one model to get the prediction, you can use multiple models. However, there are different designs of the ensemble model. There's a bagging, which is the parallel one, which I will show you. And there's a boosting, which what it does is that you have a model, the first model learning, then after that the second model is learning but trying to correct the error of the first model, which is the best way, compared to bagging, which is just the voting. So you're running the models are independent of each other, they don't know the errors of each other. From there you're just averaging, which is the other ones, they may perform terrible, the other ones, they may perform better, but now you're just averaging, which can lead to a problem. And then you have also a staking. A staking is just it's just a mixing different classes. So which is in most instances, people, they tend to shy away from using the staking models as such. So they tend to use the boosting models because they're the best so far. So the core concept behind this is that one model is weak, and the best way to use machine learning models, try to use ensemble model. And you don't have to worry about how will I put models together. There are already models that have been put together for you to use. You just need to hyper tune and fine tune them, so that they can work properly for your own data. So I'll start with the random forest, which is the baking method, the democracy one. So what you do is that you have random trees, which is based on decision trees. Of course, I didn't talk about decision trees, but the decision trees is like, for instance, if you see the first node is that if it's red, go this side. If it's yellow, go this side. Then if it's yellow and has a let's say we are talking about the t-shirt. So how does it learn? It's going to say if it's red, let's go this side. If it's yellow, go that side. Then if it's yellow and has a cartoon in front, then go this side. This is how it's learning. It's learning based on a tree. And the longer you make your tree, the better sometimes, or the worst case scenario, depending on how your data, how complex is your data that you're trying to input. So what is interesting is that you can use up to many trees, hundreds of trees that are learning in parallel. And from there, what you're going to do, they're going to vote, which means if you're doing a classification, but if you're not using classification, you're doing prediction or regression, they're just going to average, and you'll get probably the best value, because I believe most of them, they're different trees, of course, and they will perform differently, which you're going to have a little bit of improvement compared to when you're just using one model alone. Then we have the boosting method, which is the most used within the industry, because you don't have to worry a lot about it. How does it work is that it uses a tree. Of course, the first tree learns and find its error, and those errors, they continue to go through the models, the data. Then the data now, the model now is trying to improve from the previous model. So those errors now, they are few, and as you go on, is that you find that the errors, they reduce a lot. So it's just like um, in a simple terms, that it's just learning from the previous one. And in such cases, so whenever it finds a good improvement, it just keep on putting into the averaging, or the final weight to it, so which is applicable to the predictions. So XGM Boost is good when you're working with different data, especially when they are nonlinear, because you don't have to worry a lot about many things because it's many trees, then they learn from each other's errors, then they improve, which is a very good idea. Then now let's go to the most powerful model of them all, is neural networks. Of course, those models that I was talking about is the one that you use when you are dealing with spreadsheet kind of data. But now when you are dealing with data that are difficult to process, such as language, audios, images, which is in this days, they are called computer vision. You're trying to either generate data as well. So now you need a strong guns, which is your bazooka, your neural network. And building them, they are not easy, by the way. Of course, the ideology behind them is that you use neurons and you put neural layers across. And depending how many layers do you put within your neural networks, um, it needs to be depending on the complexity of the data. Because if you put too many neurons, then now your models will underfit because the data is too small for it. So it's really unnecessary. And neural networks can perform both classification and regression, depending, or even generate data itself. So which is quite um, 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 a brilliant thing. So I hope I'm still on time. Just to summarize of what the what models can you use. So when you're dealing with simple trends, where now you understand simple trends like within your data, you can see them. You can use linear regression, especially if they are linear. And and then if you're trying to do classification, you can use SMV. But of course, the SMV, if the data is a bit complex, it will fail a lot. You'll get high error, so it won't be that accurate. And when you have messy data that is nonlinear and it's difficult to generalize, you can use random forest. It's quite stable. But if you want good accuracy, then you can deal with XCM boost, which is a very good thing. Then from there, you can do your neural networks if you're interested in generating images or classifying them, or maybe you are trying to do self-driving cars where they need computer vision. So you need to train your models using neural networks so that it can know this is a road, this is an object, this is a person you shouldn't run over. So those are the things that you need to remember. So overall, you just need to know what type of the data that you have is important to understand the data you have before you choose the model. And just know that ensemble models, they're very good. And especially you don't need to use neural networks um, unless it's necessary. You don't have to complicate your work. Such simple models such as ensemble models and single models, they do work fine for machine learning model, and it's not a bad thing or to use them. Uh, so what I'm gonna do, let me try to move this to the other side so I can see. So there are many packages within Python that we use for machine learning models. So we also have NumPy. NumPy is just for computing it, and many of the machine learning model packages, such as your sklearn, they are built using NumPy. So it helps you to write equations and everything. So you have pandas. Pandas is to have you see your spreadsheet to be visualized less easier compared when you are using dictionaries, because most of the data can be stored as dictionaries. So you have pandas that can help you to visualize and also put it in a proper CSV format or your spreadsheet. Then you have matplotlib, which is for sketching, and your seaborn also is for visualization. Then you have sklearn, which has many of the models and many of the functions that you want to use when you are splitting the data and so on and so on. And you can also call the models from your sklearn. And you can also use their functions to evaluate your model. So it makes things very easy. You don't have to write a code from the beginning. So we're just going to first start by importing all the packages that we think they are necessary. And what we're going to do, I chose the Boston housing dataset because I've never used it before. So I wanted I want a surprise for myself as well. So we'll just see how far it goes. If we get it wrong, so I'm not alone. So it means all of us we getting everything wrong. So what we're gonna do, we're just gonna upload the data set. So your sklearn also have data set as well that you can use to train and see how how to apply your model or train yourself to build machine learning models. So now, as you can see, I just said Boston Fetch OpenML, the name of the data. This is the name of the data set. Then the vision is the first vision. And then as a frame, I want it as a frame, which is gonna put it as a dictionary, I would say. So as you can see, is a dictionary kind of frame. So this is not good for visualization. So you can see it's difficult for us to read. From there, what I will just use, because I've imported pandas, then I can just convert everything to a proper data frame based on those data so that I can be able to visualize the data properly. So let me just say df. So now I can show you how does the data shows. Now I have my data as rows and columns, so which is now nice. Of course, I don't know the data yet, but if you don't know your data yet, here is being explained here. If you're gonna use, so a person who's putting a data in need to explain what does each variables on the column mean. So which are here, but I copied some of them down the line so that we can visualize them properly because it's a little bit messy there. So to understand the shape, of course, you can also do data df dot shape, which tells you how many rows do you have and how many columns. Of course, this is a simple way. This is a simple data set. It's not a complex. So you have only 14 columns. So which is going to be quite easier for a linear regression. And then we can list the number of the variables that we have. Of course, they are being abbreviated. We don't know yet. And now this was just to show the data here, of course, but I don't think it's necessary now. So, but here I just copied all those things that you were seeing there. So CRM, which is this one, is the crime per capita, is just how much of a crime within the region. So this data set is about the pricing model of the Boston houses. So this is how much of a crime is there. This is the proportional land zone. So the CN is the proportional of the residential land zone for lots of, which is the ones that are greater than 25 square feet. So they're using square feet. Of course, now you also have this one as well, which is the retail business. So what are the business next to the houses? And also you have the Charles, if your house is close to Charles River, then it's 1. If it's not, then it's 0. So then you also have nitric oxides, what is the pollution within the city? And you also have the average number of rooms per house as well. Now you have the age of the house. Now you have the distance from the employment center, the distance from your CBD where there's a working, those CBD where people are working. How far is the house? And you also have an index accessibility. How far is it far away from the highway? And you also have the tax of the property, and you also have the teacher per ratio in town. I don't know if this is a necessary for us to train the model of, but I don't know. So which is interesting. We'll see. So then you also have B. I don't know if they really influence the price, but maybe it does because if you have kids staying within the town, it means the town is livable, then they can increase the price. I don't know. I don't know. I didn't do commerce. I don't know how would they price the house like that. So, and you also have the B, which is the proportion of the blacks by town. And you also have us here, which are the ones that are earning lower age, the percentage of how many people are, the percentage of people who are earning low wage. So you can tell if the people who are staying in this town, they're earning less, it's likely that the houses are not expensive. So that already tells you something. So now this is the prices that we're interested in. However, they're reported in thousands. So if it's 90K, if it's 24, means it's 24K, which means 24,000 USD. So that's what we have. So now what you need to understand is first, let's describe our data. Let's try to see what is the most expensive house goes for. So this is your prices, and your most expensive house goes for 50,000. And 75% of the houses, they cost less than 25,000, which is interesting. And if you're wondering how am I seeing this, this is your 75%, and 50% of the houses then they cost for this, they call less than this. Then you have a standard deviation that tells you the difference price range within the houses. And you have discount, it just tell you how many data, how big is your data set within the spreadsheet, which you have about 506 rows. So we're just gonna go further. Then we're just gonna plot the distribution. And of course, before I will just pass in quick, but as you can see, the distribution, the mean lies here within 24,000, around 24,000. But sometimes you may find that something happened within the city. Now the houses go for way less. That's called data drift. And when the data drift, it makes your model worse. Now it will predict things that are not good. And such things is something that people run into when you are a machine learning engineer, because you automatically just automate your model and deploy them there. But when the data drift, you don't know. And that's going to result into a problem. So you just need to go and check it on and keep on hyper tuning your model until it's good. And of course, this is also explaining the same thing here. I'm just trying to visualize the outliers, which are these guys here. So, okay, then now just gonna look what is important first. And first, we need to check how many columns or rows they are empty within our data frame. Luckily, because this is already prepared properly, then we have zero of the columns and rows that are empty. So we are happy with that. And types of data that we have, whether they are integers or float, it's a good thing to have floats. And then here we have float, but we also have categoria, which is this one which I was telling how far is your house from Charles River. If it's far, it's gonna be one. If it's not, if it's if it's far, it's gonna be zero, and if it's close, it's gonna be one. It's a categorical thing. It's either A or B, so it's categorical. So then from there, now what I was just trying to do is just to look at the relationships, because my intention here is to try to use linear regression. So let me just try to visualize the relationships here. So I can see I'm happy with the correlation. There's some correlation here. With the RM, these are number of room per house, which I've expected it that when they are pricing it, the rooms should counter. Whether the house have 5 rooms, then the price should be that. And this here, what you're also seeing is what I was talking about, us who earn less. So if there's too much percentage of people who are earning less, then the price, if there are less people who are earning less within the town, the price is very high, which means there is rich people who are staying there. So it's just tell you about that, which is very, very informative. Then we're just gonna continue, of course, just print out the correlations properly. Then we just can see that we have good correlations here. And we also have negative correlation, but this is still good because there is correlation. What matters is that because there's correlation, we know our linear regression will work. So I'm not going to do many things now. I'm just going to continue and try to split my data so that we can go into training so I don't run out of time. So now what we're going to do when we build a machine learning model, we create a training set and also a a test set. So what we are trying to predict here is the prices. So, which I think I skipped here. So you can see here I dropped this column because it's what I'm trying to predict is my y variable, what I'm trying to predict. So if I leave it there, it will introduce a data leakage because now it's going to know the values. So we're going to train them based on X and try to see if they can really find the Y variables for that. So now we're going to cut our data into, I hope I didn't. So we're going to cut our data into 70% training and 30% test. And we don't have a validation set because I'm not intending to fine-tune the model. So now I'm just going to call the model linear regression. This is activation of the model. And now I'm just going to feed the model. This is training. And you will see how fast it is to train. It's done training. So now what I'm just going to do, I want it to predict my Y trains when I put my X train. And now I also want it to predict my Y test when I put my X test. So just to see how accurate and so I can evaluate it. So we're going to evaluate it using the R squared, and you can also evaluate it using the MSE, which is mean square error function. So we're just going to print it out here. So if you can check, I didn't do anything at all. I just separated the data, trained the model, and this is the accuracy that I'm getting. So 74%. So it can explain 74% of the data within the training, and also the test is still 71, which is not terrible at all, which is still good. But now, can it help me to interpret what was happening in that data? Of course it can. So now we can compute coefficients. What do coefficients tell us? It will tell us how did these people rate their prices. So now it tells us if one room, it goes for 4,000 USD. So if you have a house that have 5 rooms, it's going to be 5 times 4, which means now we know. And if it's close to Charles River, it's going to cost 3,000 more. I mean 3,000 USD more compared to when. And of course, when you are close to how far you are with the, but the crime does not really influence the price a lot. So what influenced the prices? It was just how far is it from the river, which I think is because of the view, and how many rooms does it have? And you also have, if the place that you are around is very, very polluted, then it's going to decrease a lot of price. Then the house they tend to cost 15,000 K, way less. Even the house is good. So this now tells you about the to be able to interpret your data now. Now you can tell things that we were not going to be able to tell when we were just looking at the data. So now what we can try to see, we can try to check the actual values of the train and the actual predicted. How did it predict? So if there were a lot, if there were scattered here within the line, the fitting line, so it means that it was performing very well. But because it's 74%, you can see there are some outliers there and so. So even the test said we're just going to visualize, but I will try to move first because I think I've run out of time. So this is the same, but now there's something that calls we do for, which is called residual test residuals. We are visualizing residuals. So if this tells us for which points they were under predicted or over predicted. So the ones that they are over predicted, they are below, and the ones that are under predicted, the data points are above. So that tells us which points did the models get wrong. So if you're interested to know which column was this, you can know that. So which is very, very interesting because now you know how to rely on your model, whether it gets, which one does it get right and which one does it get wrong. And then, of course, now there's something called multicollinearity, which tends to make the model perform less. What we mean by multicollinearity is that when you have high correlation within your X features, let's say your age and your crime, they have correlation of 0.9%. That introduce multicollinearity within your within your model, and it can make your model to perform poor, by the way, if you're using a single model. So that's something that people, they don't really check a lot. So how can you check it? You can just compute things that are called variance inflation factor, where now if it's greater than 10, if the values are greater than 10, then it means we have a problem. So now I'm just trying to check where my features, you can just ignore the constant, and you can just look at the features that we were using for training, and you can tell none of them is even greater than 5, which means we don't have multiple linearity. So of course I'm moving fast. And of course, here I was just trying to check which one is more strong, the strong correlations, which we already computed them. And now, as I was saying the other time, I told you that, hey, when you have this model and you have a weak correlation, it means your model may not, there's a saying that the linear model won't be getting anything out of it. It can be a lie depending on the data. Because now what we're just gonna do, we're just gonna remove the one with a very low correlation to the prices, which is this one, which is this variable. We're just gonna remove it, and we're gonna try to fit the model and train. You'll see the accuracy. So I just removed this one variable here, or this one feature, and I just wanna see what will happen when I remove, because it doesn't have high correlation with the prices. Look at the test now. It's terrible, and the train is terrible. So as I was saying, that it's very important to understand your data complexity, because the data is not complex. And now what happened is that the linear regression model is trying to leverage each and every data that it can use to predict, to make the predictions. And now we're just gonna move a little bit faster and move towards PCA. So because you have a data like this, and now what you can use as well is a principal PCA, where now you're just going to reduce your data and use principal component to predict. So when you use your data, when you use PCA, you need to transform your data cell or scale it. Scaling it, it helps the models to learn faster compared to when you are using raw data for PCA. So what we're going to do is that we're going to generate a PCA. I'll just show you something. So now the PCA managed to generate 5 or 12 columns. So what it's telling us here is that 2 of the columns that it generated when it was scraping the data and tried to reduce it, they explain 60% of the data. And then about 10 of the features, they explain about maybe 95% or 90, I don't know. I think it looks like 98. Then which means the rest of this is just noise. So you can use PCA. Let's say you had a huge data, maybe you had thousands of columns, and you are trying to reduce it so that now you can put it within a linear regression model to make prediction. So you can use that. This now will becomes your columns, and you can just feed them properly within your data. This is just a visualization between PCA1 and PC2, which explains 60% of the data. Then from there, what we're going to do, we're just going to take the features that explain 95% of the data from the PCAs, which there are only 9 of them. We're just going to take 9 features and put them into training and see if we can regenerate the accuracy that we were generating when we were using the raw data. As I was saying, when you use PCA, you lose a lot of data. The information, you can see now the accuracy dropped from your 0.71, which was your test before, now is terrible now. You have a 64% accuracy, which is terrible. So because I'm moving fast now we're just going to try random forest. And of course, I'm just going to do the same thing with random forest and also the XGM boost. I just want to show you how the accuracy changes. This is what I was telling you about, that in sample, they work magnificent. You can see with the random forest how much of the accuracy you are just getting, which is 88.87% of the test, which is very, very good. And now let's try of course, let's try the XG boost, and you can see the accuracy is 89%. So which means your model is a little bit or more accurate compared to linear regression, and which means it's also learning from those small and non-correlating data towards your prediction. Then, of course, this is just the same residual that I was explaining before, that now you have most of them now concentrated on zero, which means that a lot of them, they are not under predicted and or over predicted. So the next time we're looking at how do we test the bias and how do we fine tune the model to be even more accurate, to move from 89% to 90 something percent. And we'll also try to build a non-biased corrected model. And from there, we'll go into explainable AI. How does now can we see how does the model learn and get this data across? I think I'm done. Thank you.